Okay, so let's go. So welcome everybody to this math reading group on information geometry. Specific, so essentially uh, differential geometry tools and theorems and theories applied to statistics, but not only statistics, but that's mostly what we'll be talking about today. So the reading was a bit dense, I thought. So if anyone survived through it, props to you. So in this, I won't be talking about everything that the document covered because there's a lot of it, mostly the key details, and also a few bits and bobs that I gathered from other sources. So I think someone posted something by John Baez that was interesting, had some nice proofs. So yeah, let's get started. So the motivation for why we should care or want to try to apply differential geometry to statistics. So roughly the idea is that we want to be able to take a space or a family of distributions, specifically parametric distributions, for example, the normal distributions, and we'd like to be able to talk about it as if it were some kind of space, specifically a manifold. And one like easy tool for that is something called the Fisher information metric or information matrix, which like already comes up very easily in basic statistics course and can actually be interpreted as a Riemannian metric, but actually like it's not the only metric, or it's often the metric that we use, but like there's a lot of variation and choice possible in here. But for applications, so one major one is actually so the Cramer-Rao bound, which is like a classic result in statistics about like the minimum variance of an estimator from a parameter. So we'll see about that. And actually, the proof by Rao, it's like a 13 pages paper, and he does use this like differential geometric argument for it. So like it's not a new thing, but it turns out there's a lot of applications. It's also useful if you want to be able to speak about distances between probability distributions, um, or maybe almost distances. So like we often use divergences, which are not quite distances, but almost. And also maybe you would like to be able to interpolate between two distributions and do that through the shortest path. And if we have a manifold with the appropriate structure, we can do that easily, or at least easily in theory, maybe not so easily in practice. So the rough outline is I be giving a bit of a recap on the differential geometry we saw and maybe didn't see over the last year. Then I'll be talking about the Fisher information metric, and then more broadly about statistical manifolds, although I very briefly, and then even more briefly about divergences, because that's about when I stopped having time to write my slides. So yeah, feel free to interrupt with any questions, and also if there's anything in the reading I didn't cover you want to discuss, go ahead. So let's get started. So to like go back to the basics of differential geometry, right? The main object was something called a manifold, which is essentially a space of points that are connected to each other, and there's a bit more structure. Specifically, I can zoom in on any point of this space, and it should look like a Euclidean space, vector space. So idea it's imagine a smooth surface, right? If you zooming very close, that it looks flat to someone, like to an ant moving around in it. And so formally, we say that for any point, we can associate the tangent space of like very tiny infinitesimal displacement along that point, from that point, and those should still like give us like lead us to some other point on the manifold. So to any point, there's a vector space called the tangent space, and generally all these vector spaces will be the same dimension, but they won't be the same vector space. So the tangent space at one point is not the same as the tangent space at another point. That's one thing to deal with. And we have generally, at least for Riemannian manifolds, a structure that lets us take inner product on vectors in the tangent space called the Riemannian metric. Is defined as this. So just characterized by some matrix G that's, or maybe not quite a matrix, but essentially a matrix G that tells us what to multiply the coefficients of our vectors. And note here that, okay, these coordinates, right, these vectors, they depend implicitly on whatever coordinate system you may have on your manifold here. And really, there's arbitrary many, like for example, even for Euclidean space, you can have the Cartesian coordinates, but you can also have the polar coordinates. And so these are two equally valid coordinate systems, but they'll give you different things depending on what you're trying to do. And the nice thing about this metric is that we can use it to compute the length of a curve or a path along our manifold. Essentially, we like take our path, integrate from the beginning to the end, and simply take the norm of the velocity of that path. So assuming, of course, that this path here is differentiable. Now, that's not the only thing we can have on a manifold. Um, Specifically, there's another structure that's at least in principle independent from a metric, but we'll see that it's nice to be able to play with both. And that's called an affine connection. And the idea is that, remember I said that the tangent space at different points are two different spaces, so by default we cannot really talk about them, especially, and sometimes we would like to. And so, for example, maybe I have a path here that goes along my manifold, and then at some point P in that on that path, I have some vector in the tangent space, and I would like to be able to like translate it or move it to the tangent space at another point P prime. And so the key idea of that is to use an operation called parallel transport, which magically like gives me a new vector that in some sense is the image or the yeah my is essentially my vector v at point P moved along so that it's still parallel in some sense. And really, like this could be arbitrary. So generally we do that using something called so connection coefficients. So this gamma kij here, and we'll see exactly what it means just now. But roughly the idea is that, okay, if I move just a tiny little bit, it should, like my new vector vp should still be very close to v, so it's still v, plus maybe something that should be linear in terms of vp. And so this plus thing that we add is what essentially this connection coefficient. So roughly, I won't go back too much into it. Once we have these connection coefficients, we can do a lot of things. First of all, we can like generalize the notion of derivative of, like we can take the derivative of a vector field with respect to another vector field, and it's defined as this. And so really it all boils down to these connection coefficients. We can do parallel transport, as mentioned. We can also compute geodesics in the sense that we'd like to have the generalize the idea of a straight line, right? A straight line, you never change direction, you stay parallel with your own. And so that's the definition of a geodesic. It's simply a curve, gamma, such that its velocity is always parallel to itself. And also, but that's something that we didn't cover then, and we unfortunately won't be covering too much today either, is notion of curvature and torsion. But note that the notion of an affine connection and the notion of a metric are not like they don't have to play together by default, but let's get to that. So if we want to be able to play with both a metric and an affine connection, well, we'll say that a connection nabla is compatible with the metric G if the following condition holds. So we're taking the derivative along a vector field Z of the inner product X and Y. So you could replace this inner product by the G metric that we have that is hidden here. If we can express it as essentially some kind of like derivative rule of a product, right? It's the product, right? You're taking the derivative along z of a product xy, and we have the product of the derivative of z along z of x and y, and the product of x and the derivative of z of y along z. Now, okay, if we do have a connection that plays nice with the metric like this, the nice thing is that the parallel transport will preserve the inner product. So if I have like two vectors u and v, and I parallel, like I move them both to another point using parallel transport, then their inner product will be preserved. So that's a nice thing. Now, there's actually a lot of many possible connections, but there's not like a nice theorem from differential geometry is that if you want a symmetric connection, so mainly saying that Kij is equal to Kji. Another word for that is torsion free, but again, I don't really have time to explain what torsion is, nor do I have a good intuition for it. And then actually there's a unique connection called the Levi-Civita connection that is compatible with G. So if we want both something that's metric, so compatible with the metric, and that is symmetric, there's only one of them, and it's called the Levi-Civita, and we'll write him with LC here in the upper left corner. Okay, so I do have like a very brief explanation of what curvature is. It's not great. I'm very sorry about that, but the rough idea is that curvature, first of all, depends on the connection. So you could have the same space, pick a different connection, and have a different curvature. But for example, if you take the sphere, okay, intuitively the sphere is curved, right? And the way you know that your space is curved is if you do parallel transport along multiple paths but that get to the same endpoint, your vector does not get transported in the same way. So for example, if I start with this vector here, right, I start at this point, and this is the vector that I want to parallel transport. If I go along this path, well, okay, it goes along this, so it bends. And then along the equator here, let's say this is the equator, it stays essentially the same direction, and so it ends up like this. But if I instead went along this path here, this blue path, then actually the vector does not get modified, and so it ends up like this. So interestingly, like depending on the path you choose, your vector is going to be parallel transported in a different way. And that's usually a sign that your space is curved. And in this case, for example, the sphere, we say that it's positively curved and that it has, in fact, a constant curvature. In contrast, you could take, for example, a cylinder. So a cylinder is a circle times a straight line. In fact, the cylinder has zero curvature, it's flat. And so regardless, regardless of the path that you took, it would actually still end up with the same result. An intuition for why the cylinder is flat is that you could cut it in one direction here and flatten it into a sheet. And you cannot do that with the sphere. So that's the very brief, like no formulas explanation of curvature. Uh, I think it's better than they keep it like this because there's quite a lot of different curvatures that you could play with, and yeah, so let's leave it at that. Okay, so let's get on to the like first example of applying this to statistics. So assume that I have some parametric family of distributions. So theta will be my vector of parameters, and I'll be defining the matrix Gij. It depends on theta as the expectation at theta. So just in case this notation might be confusing, like I'm not taking an integral over theta, I'm just taking an integral over the domain of my distribution, but for the value of the parameters theta. And so I take the expectation of the ith derivative of this function, which is simply the log likelihood of my distribution. So taking the ith derivative and the jth derivative of my log likelihood. I think, yeah, probably that's sort of missing. I think this should be p theta here. So I claim that this matrix, which is defined for any valid vector parameters, is going to be a symmetric positive definite matrix. And so because it's symmetric and positive definite, we can actually use that as a Riemannian metric. There's no reason why not. And so, for example, let's take the normal distribution. So normal distribution, we could parameterize them by mu and sigma, or maybe mu and sigma squared. Yeah, there might be confusion in the reading about the exact parameterization. So there might be mistakes either in here or in the reading. I'm not sure which. So let's say I parameterize my normal distribution by the mean mu and by the variance sigma squared, or the variance. So we know the value of that. Then if you do the computation, which is not so easy, but trust me on this, this matrix Gij, or the metric, is going to be a diagonal matrix with 1 over sigma squared uh, for the mu, so the mean, and 1 over 2 sigma to the fourth for the variance. And so actually like this matrix, so it's diagonal, so it's nice, but because we have 1 over sigma squared in the bottom, this actually turns out to make the space of, like if we were to take like the Levi-Civita connection, this would make this manifold a hyperbolic manifold, but that's more for fun stuff. So actually, let's dive into some applications. So I'm not sure how much you guys know about like statistics and like sufficient statistics, so this will be very light. So like one of the main goals of statistics is that you have a distribution and you like to be able to estimate the parameters. Let's say you have a sample and you like to find out maybe the mean and the variance of your normal distribution. And so to do that, there's a whole theory of like statistics and what kind of function you need. And for example, if we have some arbitrary function f of x, and we call the result of that y, which is a new random variable, assuming that x has the distribution p x theta, we can always factor p x theta as a function distribution q of f of x that depends on theta, and then times some kind of rest reminder r times x theta. And if it happens that this r function here does not actually depend on the parameters, it only depends on x, then we say that f of x is what is called a sufficient statistics for x, and that means that if we want to estimate our parameters, really f of x is all we need. We don't need the rest. So a nice theorem to sort of like make that formal. Let's say G of theta is the Fisher information matrix for Px, and we call G underscore F, it's not super clear here, G underscore F, the Fisher information matrix for the distribution of f of x. Then we have this inequality, but it's a matrix inequality, so G of F theta is smaller than G of theta, because those are matrices. That means that uh, this difference, G of theta minus GF of theta, is a definite positive matrix. And so actually what this tells us is that it basically tells us that when we look at only the distribution of f of x, we're possibly losing information about the actual distribution of x. But if f is exhaustive, we have all the information, and so actually the difference is 0. So actually, let's get into the proof for that. So again, we'll be a bit brief. So we can write the Fisher information matrix for g of f as the following. And then since we can factor p as q times r, then we can also factor the log likelihood and express it as the sum of q plus the sum of r. And then when we take the derivative, that still works. And so another point is that, okay, taking this expression, so the ith derivative, not the ith, the derivative along j, of the log of q, that's actually the same as the expectation for theta of the log likelihood conditioned on y. And the proof for that is a bit short. It's simply that if we have b, like the set of values we're integrating over y, we can just transfer over, take, oops, the inverse image of it and get the log likelihood in the end. If you don't understand this, that's not a problem. I'm not entirely sure I understand it either, so you're in good company. But roughly that tells us that the expectation of this quantity of, so the derivative along I, or coordinate I of log R, condition of f of x is 0. And what that means is that, okay, this function here is going to be orthogonal to any function phi of f of x for this inner product on the bottom here. And roughly that means that the information that we're losing by only looking at the distribution of f of x is given by the following. And so it's the expectation along theta of essentially di log r, dj log r. And so that's the covariance matrix. So it's the expectation of a covariance matrix that's conditioned. And so the covariance matrix is always positive definite. And so this thing here is positive definite, and so we have this inequality. And of course, if r does not depend on theta, then these derivatives are all 0, and so that works. And so the equality is reached. So all that tells us is that if you have a sufficient statistic, really you don't lose any information by only looking at that. Okay, so another important theorem, I won't delve into the proof because it's probably even less intuitive, but the Cramer-Rao bound, it tells us that if you have an unbiased estimator of theta, so theta hat, unbiased just means that the expectation of theta hat is theta, so that's the important assumption, is that it's unbiased. Then the variance of it is at least the inverse of this matrix. And so notice here again it's a matrix inequality, but we can always sort of get back to like a scalar inequality. But why is this important? It tells us that, okay, you want to estimate a parameter. Okay, unbiased is nice, it's important. And if you had to choose between any two estimators, you'd probably like the one that has the smallest variance. But this theorem also tells you that there's a minimum variance you can hope for. And so if you know that, if you have an estimator and you know that it only has the minimum variance, then you know that you cannot really improve over that. So yeah, I'll skip over this proof here because it's not super clear. Okay, any questions so far? I see that we've lost quite a few people. Okay, so let's keep going. So we talked about the Fisher metric, the Fisher metric, but what about the associated connection? So I claim that if you define these so Christoffel coefficients as the following, so the expectation for theta of this expression, those give you actually the Christoffel coefficients of the metric connection associated with the Fisher metric. So it's the Levi-Civita metric for the Fisher metric. So that's nice, but maybe not super insightful. It's nice to define this, and we'll see them later a little bit, something called the alpha connections. And the idea is that you take some alpha in the real numbers, and you construct a new connection from the first connection simply by defining new coefficients. So it's essentially the same expression, but instead of 1/2 here, we have 1 minus alpha over 2. And so taking alpha to be 0 gives us again the Fisher information matrix. Uh, metric. Sorry. Why these are nice, we'll see just now. So there's a theorem called Chen-Xiao theorem that basically tells us if you have a model S, so a family of parametric distributions, you have a sufficient statistics f of x, and then the induced model or distribution S of f, sorry, then we know that like this, have this factor r that disappears, so the log likelihood of S is equal to the log likelihood of f of x or SF. And so that means that in particular the metric and the these connection coefficients are going to be the same. And so they'll define the same geometry. And so there's this theorem by Chen-Xiao from 72 that says suppose that G and nabla, so the metric and connection, are invariant for sufficient statistics, then there must be some scalar C in R and some alpha in R. Actually, C must probably be positive, I guess, and alpha in R, such that CG, so basically it's a multiple of the Fisher metric, and the connection is one of these alpha connections. So essentially that tells us that the Fisher metric is unique in some sense up to a scalar factor. Okay, so that's for the Fisher metric, but maybe we'd like to be able to play with other kinds of connections. And so a first step to generalize that is to, instead of having only the Levi-Civita connection, we'd like to have a connection, but maybe, yeah, we have to have different connection, but still play well with the metric. And so to do that, let's say we have a manifold with metric G and connection nabla, and nabla doesn't necessarily have to be compatible with the metric at this point. We'll call connection gamma star. We'll say that it's conjugate to nabla with respect to G if the following equality holds, and it's essentially a variation on the condition for for a connection being compatible. So now we say that the derivative along x of the inner product y and z is the first term is the same, so it's the inner product of the covariant derivative along x of y and z. And then instead of the nabla connection, we use this nabla star connection. And this must hold for any differential, vector field x, y, z over M. Again, we can just rewrite the same using the metric. One nice property is that the conjugate of the conjugate is the original connection, so essentially it's unique in some sense. And in fact, if you have a connection and a metric, you can find a unique conjugate connection for that connection. And so the nice thing is that if we now do the dual parallel transport, that again preserves the metric. So it's the same as before, but now the first vector u we transport using this nabla, and the second we transport using this dual connection nabla star. That again preserves the metric. So we're playing with two metric at the same time here, but this lets us be a little bit more flexible. And so whenever we have a quadruplet M, G, nabla, and nabla star, that's going to be called a conjugate connection manifold. Also note, if you were to take the average of these two conjugate connections, this would give you back again the Levi-Civita connection, because this would be self-conjugate and again still compatible with the metric, and so there's only one metric that connection that works with that. Okay, so the more general notion of a statistical manifold, to do that we take what's called the Amari Chen-Xiao tensor, And it's at least when you have these two conjugate connection is defined as this expression here. So it depends on the Christoffel coefficients for both connections. Importantly, this tensor here, so it is a tensor, unlike the connection, the Christoffel coefficients, which are not. It's a it's a free covariant tensor, and it's also totally symmetric in the sense that Cijk is equal to C sigma I sigma j sigma k for any permutation sigma. And so the generic notion of a statistical manifold is this manifold M, the metric G, and then this totally symmetric free covariant tensor. And the nice thing, we can generalize then this notion of, so if we have a pair of conjugate connections, we can generalize this notion of alpha, like alpha connections or alpha uh, conjugate connection manifold, sorry. And it's the same idea, so we define gamma alpha k ij as gamma 0 kij. So gamma 0 is the Levi-Civita connection, and we add this minus alpha over 2 Cijk, and then similar thing for minus alpha. And so the idea is that you have like a bit of an interpolation between, yeah, just an interpolating between your two connections, gamma star, right? Because you have, I think it's gamma is equal to gamma 1, then the opposite is gamma s1. So you have like you have your two conjugate connections, and then you can interpolate between them. At 0, you have the Levi-Civita connection, but you can choose alpha arbitrarily. And we sort of get an intuition why we want to play with alpha, at least toward the end. So if we define these connections, we get another conjugate connection manifold. We get a family of conjugate connections. Okay, so let's then move on to the fundamental theorem of information theory. So unfortunately, this does mention curvature, and I've not like explained it super well. I'm sorry again. But if we have a torsion-free, again, just remember symmetric, forget about torsion, just think symmetric connection, it has a constant curvature k, or kappa in this case, then it's the same for its conjugate connection. And in particular, so if you have these alpha connections, we know that it's gamma, so nabla alpha flat, if and only if it's minus alpha flat. Or if you forget about these alpha connections, if it like if the manifold is flat, so zero curvature with respect to the one connection, it's also flat with respect to the other, to the conjugate connection. Now, why do we care? So the reason for that, like if you focus on the flat case, flat means that the connection coefficients are all zero. And so if you remember what we said at the beginning, we said that parallel transport, you have your original vector plus a term that depends on your Christoffel coefficient. So if this is zero, then parallel transport is easy. You just copy the vector, it doesn't change. And so that says, or that means that geodesics, so like these straight lines, they're easy. They're just affine curves, and there's like it's not a difficulty. And so it's one reason why people like try to get flat connections, is that when you have a flat connection, the geodesics are easy to express. It's just linear interpolates, and so super easy. So sometimes people will adjust these alpha to get a flat space, but it's not always that you can get one. Okay, so we're moving on to the slides. I didn't have that much time to finish, so hopefully we can discuss more about that. Um, so you could, based on the, like, even if you took just the Fisher metric and the associated Levi-Civitec connection, you could define like the shortest path, and that would get you the Fisher-Rao metric. So that gives you already a distance between distributions. But there's a more general notion of the distance between probability distributions called divergence, which is even in machine learning very, very common, right? We know the Colbert-Liebler divergence, and so a divergence, at least in this context, it's going to be a function that takes 2 points on the manifold, so 2 sets of parameters, return a positive real number. In this case, it also has to be 3 times continuously differentiable. And so the first condition is the usual, so it's positive, and it's only 0 if theta is equal to theta prime. And so that's more of the like the basic. And notice that it doesn't have to be symmetric, and it doesn't have to satisfy the triangle inequality. And so that means it's not necessarily a metric. The other conditions are essentially more related to the information geometry sense. It's saying that if we take the first derivatives along each coordinate of this expression, evaluated at theta is equal to theta prime, that should be 0. And same thing with take the, I think, up, yeah. So other sense, to either input, that should be 0. But so essentially what it says tells us that on first order this thing is 0, but the second derivative has to be, so it's a matrix, it has to be a positive definite matrix. And so there's actually a nice example of that. So if we take the Colbert-Liebler divergence, here I've noted it in maybe a bit of a weird way. I fully stole that from John Bayes, who has a nice post about it. So we can rewrite the Colbert-Liebler divergence as this. So the integral over the domain of P over Q times the logarithm of P over Q times Q. So like the cheating is in this place, right? Normally you'd only have, like you'd remove this, but here I'm having it back in. And if you were to compute the second derivative of this, I claim that it's equal to this expression here. And if you look closely, well, okay, it's the derivative along the ith coordinate of the logarithm of p. So actually, that's the log, like the gradient of the log likelihood, and then the derivative along j. So this whole thing here is actually the Fisher matrix. Now, I did want to like give Bayes proof of that because it's actually interesting, although a bit evil. But we'll see if we have the time for that. So yeah, before I joined this, I just had time to finish this slide. So there is actually a way to construct a statistical manifold from a divergence. So if you have divergence function D, then define the metric as the following. So you take the second derivative of your divergence. Similarly for the Christoffel coefficients, both the primal and conjugate, then you get a conjugate connection manifold. And so it's another way you can construct a statistical manifold from something. But there's a lot more about the stuff you can do with divergence, but I didn't have time for that. So yeah, hopefully that wasn't completely messy. So let's see if anyone has questions.
I think it was good. So I actually forgot we had the group today, so I didn't didn't even do the reading.
Oops.
But I did write down at least a couple of questions. So the first one was why do we even have the conjugate connections? I guess I didn't really understand why those were
Right.
relevant.
So I'm not entirely sure myself, but I think the main reason is that if you were restricted to only the like the Levi-Civitec connection, that might be restricted because, like for example, if you took the normal distribution, okay, you have the Levi-Civita connection, but it's not a nice space, it's a hyperbolic space. Maybe you'd like to have nicer, like a nicer connection, and so that's why you try and get another connection for that. And so this like conjugate connection is a way to get away from still have a somewhat simple connection, in particular like torsion tree. Don't for, don't worry about torsion, but you still have
Symmetric.
symmetric. Sorry, so you still have a symmetric connection, but it's like you have a dual operator.
Hmm.
So I think that's the main reason why people play with that.
Okay, I'm not entirely sure what that means, but okay.
So I think maybe let's give another example. If you take like Cartesian coordinates in Euclidean space, um, the connection for Cartesian coordinates is nice. It's flat, so it's yeah, it's trivial. If you were to do the
Mhm.
same relative to polar coordinates, it would not be flat, I think. Actually, no, it's still flat, but it's a bit messier. So, like depending of your choice of coordinates and depending of your choice of connection, you can get a flat manifold where the like computing the shortest path is super easy. So I think
Okay.
usually the why people might care is that you choose like for example this alpha parameter so that your metric or connection is super nice and you can work easily with it. Maybe like find some easy statistical test.
Right. Okay. Thank you.
Okay. Any other questions? Okay, I saw you, Nev. Do you have a question?
Yeah, yeah, I'm going to have to watch this because I kept disconnecting the entire time, and
Ah,
even when I was connected, it was yeah.
yeah, I think I probably, I mean, regardless of whether we go back to this, I should probably make like a differential geometry session just on curvature because that was the big thing I tried to avoid here, and it's difficult. So, okay, but yeah, I'll pause the recording soon-ish. Anyone else has questions? Okay, apparently not. Okay, secondary question. Among the people who did read or did some of the reading, how digestible did you find the main reading? Okay, I'm going to interpret that as most people not having done much of the reading, or let's see. Okay, I wasn't looking at the chat. Oh yeah. Okay, now I see the chat. So yeah, of course I was using Einstein summation all over the place. So hopefully that was fine. Uh, yeah, visual differential. Okay, maybe one question. Okay, so I personally don't know differential geometry, but I'm okay with semi-definite matrix and okay with some filter statistics, so I couldn't really understand the reading, but I see how it might be important and useful. Yeah, I mean, honestly, this reading is a bit dense, and the order in which they present things is not great. Like they start all immediately with the big nasty differential geometry, and they don't give like the neater examples first. I guess this isn't really a fully formed question, but I was wondering if parallel transport could be applied for latent walks, as in, for example, in kind of latent diffusion models, or yeah, I think so, but the problem is that you need a way to like know what your connection is in your latent space, and I think the assumption would be that it's usually just the flat connection, so not super interesting. And also the sad thing is that depending on your connection, computing the parallel transport is solving an ODE, and so that can get expensive. Because yeah, interpolation is the latent space field reducing integers at times. I mean, I don't think it's a magic solution, but actually, if you look at the reading, they give some applications, and for example, they compare so natural gradient descent, and that's actually the same-ish as gradient descent, but on your manifold. But it's much more expensive because you have to like multiply by the inverse of metric, and so you have to solve a linear problem at the same time, and so it's much more expensive, especially as expensive as the Newton method for what's equivalent to just the gradient descent. So, but yeah, maybe some. I mean, if it's only like a actually, I think if it's just like a small latent space, like not too big, that's fine. So yeah, maybe that's something you can do, but I wouldn't be surprised if Arthur has tried that already because she tries everything. Okay, so yeah, she very probably has. Okay, so I think if there's no more questions for now, yeah, maybe a small one. Yeah, at least my apartment is getting warmer because I'm stressing. Yeah, so yeah, if there's no more questions for now, thanks everyone for coming and thanks for the appreciation. I hope you got something out of this. Maybe we can like do it again another time, but with more preparation this time. So yeah, thanks everyone.